Hello, my name is Julia with Support Princess Tutoring, and today we are going to look at an example involving dynamics with a focus on kind of work and energy. So for this problem, we have a little girl and she's pulling a sled across the snow. She pulls the sled at an angle of 20 degrees with the horizontal. The sled has a mass of 30 kilograms and the coefficient of friction is 0.6. She is pulling the sled at a constant velocity. And part A asks, what is the tension in the rope? So the first part is, let's just kind of like draw a picture of what's going on and kind of what we know here. So we have this sled and we have this little girl. And it says that she is moving with a constant velocity. And she's pulling the sled at an angle of 20 degrees with the horizontal. And it also tells us the mass of the sled. So it says the mass equals 30 kilograms. And it gives us the coefficient of friction here, mu, which is 0.6. And that's all. Right? It doesn't tell us anything else. So let's go ahead and draw a free body diagram. Again, step 2, we're going to draw a free body diagram. And this free body diagram should include essentially all of our forces that are acting on this sled. So we have gravity. And for right now, we are on a level surface, and so gravity would be pulling straight down. And then the sled isn't falling towards the center of the earth, and so we have the ground that would be pushing up on the sled an equal and opposite force, known as the normal force. And then we have this rope that's at an angle that is providing tension, or also what we consider a pulling force. And I'm going to put in here that that's at 20 degrees. And we're moving at a velocity here in this direction. And then what about friction? So it didn't tell us to consider negligible friction, and for that, furthermore, it gave us a coefficient of friction of 0.6. And so our friction should always be directed in the opposite direction of motion here. So we have a force of friction there. So our tension and our force of friction are not necessarily in exact opposite directions here. And that's all of our forces. And so we need to kind of fill some numbers in here. And so let's kind of go around our free body diagram and fill in all the numbers that we know. So for our gravity, here our force of gravity is always equal to the mass times the gravitational constant. And so it gave us a mass of 30 kilograms. And then we can put it in 9.8, and that would be meters per second squared. And so let's go ahead and calculate that. And I seem to have misplaced my calculator. There it is. You can also use a value of 10 instead of 9.8 to make your calculations easier as an estimate. So we have 9.8 times 30, which is 294 newtons. Okay. For our force of friction here, our force of friction would be mu times the normal force. And we don't know the normal force at this time. Now, the tension here is at an angle, and so that means that there's kind of two components to this tension. You could think of it as a component here in the horizontal direction. You could also think of it as a component here in the more vertical direction. And if we want to calculate those out, we would have this kind of being our y, this kind of being our x. Our y here is the side that is opposite our angle. So if you remember your SOHCAHTOA, opposite over hypotenuse is sine here. So if we have sine of 20 degrees, that would equal to the side opposite, which is y, divided by the hypotenuse. And then I'm going to go ahead and just multiply by the hypotenuse here so that we have a single equation. So we have y equals tension times the sine of 20. And for x here, the x is the side adjacent. So COA is adjacent over hypotenuse. So that is cosine of 20 degrees. And again, we would have x divided by hypotenuse, which is tension. So I'm going to multiply by t there. Okay, so we now have kind of two new vectors, or the components of our tension here. And the reason that's important is because we need to kind of write out F net equals MA. And we here are not accelerating up and down, nor are we really accelerating in left or right. Our acceleration is equal to 0 because we have a constant velocity in this problem. So that means our F net equals 0. So we know that 0 has to equal the sum of all the forces in the vertical direction and the sum of all the forces in the horizontal. So for the vertical direction, we have a normal force, we have the force of tension times the sine of 20 degrees, and we have the force of gravity. So let's plug in our numbers as best we can. So I'm going to go ahead and solve for the normal force here. So if I want to solve for the normal force, that means I'm going to get negative the force of gravity minus the tension sine of 20 degrees. And let's go ahead and plug in our number for our gravity. Now our gravity is pointed down, and so I didn't put it, but I should technically put a negative here. So we have a negative 294 minus the tension times the sine of 20 degrees. And that would equal our normal force here. Okay. We don't know the tension. It does not give us the tension. So there's not anything more we can do to calculate the normal force at this time. So let's kind of look over what's going on in the horizontal direction here. So in the horizontal direction, we again have F net equals mass times acceleration, and our acceleration is 0. And that should equal the sum of our forces. And so we have pointing in the positive direction, the tension cosine of 20 degrees plus the force of friction. And I'm going to go ahead and solve for the force of friction here. So force of friction would equal to negative tension times the cosine of 20 degrees. Okay, I'm running out of space here, so we're going to kind of take these two formulas here, this one and this one, and we're going to go to page 2. So the force of friction equals negative tension cosine of 20 degrees. And we also know that the force of friction equals mu the normal force. And so this is where that second equation is going to come in. We had that the normal force was equal to negative 294 because that was our gravity, minus the tension sine of 20 degrees. So we're going to plug that into here. And we're also going to go ahead and plug in our 0.6 mu. So 0.6 times negative 294 minus tension sine of 20 equals negative tension cosine of 20. So we've done some complicated math here, but we now have an equation where our only variable is tension. And so we can indeed solve for the tension in the rope here. So let's go ahead and do that. So to do that, what I'm going to do is I'm going to go ahead and move this term to the other side of my equation by adding it, but we would also have to multiply out the 0.6 first. So let's distribute the 0.6. So we've got 0.6 times 294. So we get negative, let me switch colors, negative 176.4 equals 0.6t, because we distributed that and then we added it to the other side, sine of 20 degrees minus tension cosine of 20 degrees. Okay, so if we basically pull out the tension here, we're going to be left with 0.6 sine of 20 degrees minus cosine of 20 degrees equals negative 176.4. So let's go ahead and plug this into our calculator here. And we're going to divide both sides by that number to solve for t. So our tension is going to equal to negative 176.4 divided by this whole thing. When you're doing this, we're in degrees, so just make sure your calculator is in degrees and not radians. So negative 176.4 divided by, and I put parentheses around this bottom denominator, 0.6 sine of 20 minus cosine of 20 degrees, and I got a tension equals 240.2 newtons. And that is our answer for part A. That is the tension in the rope from the little girl that's pulling the sled. So for part B, it says, if she moves the sled 10 meters, how much work did she do? So let's talk a little bit about work here. I'm going to go to the next slide. Let's see, I'm going to remember that my tension in my rope was 240.2 newtons. Okay, so we go back to our drawing, kind of like what's happening here. She is pulling this rope and moving. The whole thing is going at a constant velocity. So what is work? Work is basically the ability to move objects. It's the amount of energy needed to create a change in velocity. And so it's also defined as the change in energy. And as long as we don't have a change in potential energy, that also could be thought of as a change in kinetic energy. And our kinetic energy would be 1/2 mv final squared minus half e final, initial squared. But she's moving at a constant velocity, right? And so we don't really necessarily have a change in velocity here. But we can also think of work as being force times the distance traveled. And this force would be the force that's parallel. And so here, we can calculate the work from essentially the tension in the rope as the force that's parallel times the distance. And they gave us that she's moving a distance of 10 meters. And we know the tension in the rope equals 240.2 newtons. Now, this tension in the rope is the tension that's at this angle here. And so we would have to consider that in our calculations. So there is another formula for work that's not necessarily different. It's the same. It just talks about when the force is not parallel to the distance, and it's F times D times the cosine of the angle here. And so if you remember right, when we did our triangle, we said that the side that was adjacent here, the X, we used cosine for that. And so that's where that's coming from. So we can just put in our numbers here. We have 240.2 newtons times 10 meters times the cosine of 20 degrees. So let's go and put that in our calculator. So we've got 240.2 times 10 times the cosine of 20. And so I got a work equal to 2,257.1, and that would be joules or also Newton meters. So that is the amount of work for her, from the tension, for her to move those 10 meters. So it's 2,257 joules. So part C says, what is the net work on the system, and explain your answer. So we've already kind of investigated that a little bit. This was the work of the tension that we calculated right here. But if we look at the work here, we do not have a change in our velocity. And so we could also say that the overall work, the change in kinetic energy, is 0. The change in energy is 0. That means the work is 0. So, but wait a second. If the work is 0, then why did we get 2,257? So let's talk about this and kind of explain our answer. So I'm going to draw our little girl with our sled again. Okay, she's pulling this sled, right? And she moves it a distance of 10 meters. And we said that the work from the tension in the rope was equal to 2,257 joules. But this is not the only force here. This tension is not the only force. We also have friction. And so if we calculate the work from the friction here, we have force times distance, and the force is you could think of it as being parallel, or we can think of it as cosine of 180 degrees, because it's 180 degrees between the distance that she went this way and here. And we have the force of the friction here would be, we had negative 294 minus tension, which we calculated as 240.2, and times the sine of 20 degrees, So that would have been the normal force, or sorry, the normal force, yes, and then we would have times the coefficient of friction, 0.6. That would be our force. Let's go ahead and calculate that, the force of friction here. Negative 294 minus 240.2 times the sine of 20 degrees times 0.6. We get the force of friction as being 225.7 newtons, and it's negative. And so if we want to calculate the work from that, we would have 225.7 newtons times 10 meters times the cosine of 180, which is just -1. And we get -2256, or rounds 7 joules. So we've got here, if we wanted to calculate the total work, or we could also call that as the net work, kind of like we do the net force. We've got a positive 2,257 joules minus 257 joules, which equals 0 joules. Okay, I did not have to do all that math to say that it was 0 joules. I could have told you that because we were moving at a constant velocity. And if we're moving at a constant velocity, that means our acceleration is 0, and there is no change in our kinetic energy. And so our work would be 0. But we also proved it, that the work from her moving by pulling on this rope, the tension there, is equal but opposite to the work of friction here. And so the total work is 0. And she, again, has a constant velocity. Now, if she was not moving at a constant velocity and we had an acceleration here, then we would expect a net positive work from this motion. So thank you for joining me as we looked at a kind of an example of work and motion and dynamics. And I want to leave you with this. What good is it, my brothers, if someone says he has faith but does not have works? Can that faith save him? And that's James 2:14. As we go through these problems, we're talking about forces. I always think of Jesus as being kind of the force of goodness in our world and in our lives. And it's our faith in him that helps us and equips us and enables us to also do good works in this world. And so we have faith in Jesus, and that faith produces good works in us. And just like we can calculate work here in moving the sled, we get to see that fruits, those good works in our lives as we walk with Christ and abide in Christ. So God bless, and never forget, Jesus loves you.